These notes are about multiplying and dividing radical expressions. So we worked a little bit with simplifying radical expressions, and now we're going to just do some operations with them, specifically multiplying and dividing them. So here's a couple of rules. First of all, if the nth root of a and the nth root of b are real numbers, then there's a couple of things that hold true. The first thing is that the nth root of a times the nth root of b is equal to the nth root of a times b. First of all, notice I'm not taking a specific index. N can be anything. This works for square roots, cube roots, fourth roots, as long as the two numbers that we're starting with are real numbers, and that's very important. This property does not hold if we're starting with things that aren't real, like the square root of -5. But if they are real, then what this says is that we can multiply radicands and get it into one large radical, if you will. So we started with two separate radicals, and we multiplied them into a single radical. This also works for division, as long as the nth root of a and the nth root of b are real numbers. The nth root of a divided by the nth root of b is equal to the nth root of the quotient a over b. Same property, kind of. We're saying that the quotient of the radicals is equal to the radical of the quotient, again, as long as we're starting with real numbers. But that's becoming really handy, because now we can use that fact to simplify things that aren't starting off so nice. Like this example, I don't know what the square root of 8 is. I don't know what the square root of 2 is either, but root 8 and root 2 are both real numbers, so we can use our multiplication property of radicals, and we can say that that's the square root of 8 times 2. Oh, but I know what 8 times 2 is. That's 16. And now it's turned into something that I can easily simplify. The square root of 16 is 4. Notice I couldn't have noticed that without combining it into one radical using the radical multiplication property. Let's look at a maybe more involved example. The cube root of 3x times the cube root of 9x squared. Again, each piece of this on its own can't really be simplified, but let's see what happens when we combine or multiply those two radicals. We get the cube root of 3x times 9x squared, all as part of the radicand. Let's keep going simplifying that. 3 times 9 gives us 27. X times x squared gives us x cubed. Now it looks like an example that we might have seen in the previous day. I can rewrite 27 as 3 cubed, and x cubed is already written as a perfect cube. So the cube root of 3 cubed x cubed is just 3x. And notice we had to combine the radicands. We had to really multiply those before we were able to simplify. So it's usually in our best interest to do that if we can't simplify anything first. Let's look at using the division property of radicals. Same problem. I might be able to simplify the numerator a little bit, but then we still have this fourth root of 5x cubed in the denominator. So I want to think of maybe I can combine these radicals, maybe divide things first. Maybe some things will cancel out, or maybe the problem will become simpler before we try to simplify. And the more you do of these, you'll realize when you can recognize when things will immediately simplify and when they won't. Notice when you divide, 80 is divisible by 5. In fact, 80 divided by 5 is 16. So this is the fourth root of 16 times, and let's see, x to the 9th divided by x cubed. Think about what that means and what's going to cancel in that fraction. 3 factors of x will cancel with the 9 factors of x on the top, and we'll be left with just 6 factors of x. You might have learned this exponent property as we can subtract the exponents when we're dividing things of the same base. So x to the 9th divided by x cubed is in fact equal to x to the 6th. So now let's try to simplify that. I want to try to write the radicand as powers of 4, because we're trying to take the fourth root. So I know 16 is actually 2 to the 4th. X to the 6th is not a perfect power of 4, but I can write it as x to the 4th times x squared, again using an exponent property. So what can come outside? What can be simplified here? Well, the fourth root of 2 to the fourth is 2. The fourth root of x to the fourth is x. And we still have a fourth root of x squared left over. So this one wasn't perfectly nice like the other ones. We still have that radical piece left over. But notice it was a lot easier to simplify once we combined radicals and did the division. What is wrong with this picture? So we have this nice radical property, this multiplication property. Here this says the square root of negative 8 times the square root of negative 2 is the square root of negative 8 times the square root of negative 2, which is the square root of 16, which is 4. But that doesn't really make sense because the square root of negative 8 and the square root of negative 2 are not real numbers. So this equal sign is presenting a huge problem for us. If you look back at the beginning, we defined that multiplication property to hold only for real numbers. The square root of negative 8 and the square root of negative 2 are not real numbers. So I can't use that multiplication property. And we know that root negative 8 is really I root 8, and root negative 2 is really I root 2. So when you multiply I times I, and as well as the radicals, we're going to get really a negative number here. So it's definitely not equal to this positive 4. And the reason that it doesn't work is because the multiplication property does not hold for non-real numbers. So not real numbers, multiplication property of radicals does not hold. Multiplication property does not hold. I could actually figure out what that product is, but I'd have to use I'd have to use imaginary numbers and figure it out. But I just know that it does not equal to 4. Before we move on to the next piece here, let's try these exercises and see if we can find a pattern. What is the square root of 5 times the square root of 5? Well, they're both real numbers, so I can say that that's the square root of 25. Wait a second, that's just 5. Let's try this again with the square root of 10 times the square root of 10. Well, again, they're both real numbers, so I can call that the square root of 100. But wait a second, that's just 10. Notice that in all of these cases, the radicand here and here is matching our outcome. 5 is matching our outcome 5. That should make sense because you're taking the square root of something and multiplying it by itself. You're squaring it. So the square root of something squared, of course, is just going to be itself. Here I have this silly example with happy faces. The square root of happy face squared is just happy face. So that's important. You can take a radical, multiply it by itself, and you get something that doesn't have a radical in it. In other words, you can take two irrational numbers, multiply them together, and get a rational number. That's a big deal. That's not immediately intuitive. But we know that root 5 is some, ugly decimal, root 5 some ugly decimal, but the product of them, very nice. The product of them is just 5. So why do I bring this up? Our next goal is to be able to rationalize a fraction or rationalize the denominator of a fraction. What that means is we would like to get a rational number in the denominator. You might be asking yourself, why do we want to do this? And the answer kind of comes from back before we had calculators. It wasn't considered okay to leave a radical in the denominator. It's very, very difficult to divide by a radical. But it's not that difficult to divide by something that's rational. For example, if you're trying to do 6 divided by the square root of 3, we first have to figure out what the square root of 3 is and then divide that into a number. And that's a lot more difficult than just dividing by 7 or 1.5 or some nice rational number. So it's not considered simplified if we have a radical in the denominator. An expression is not simplified with a radical in the denominator. So how can we get rid, and we have 2 examples here. Let's look at this first example in black. How can we get rid of that root 3? What could you multiply the square root of 3 by so you get a rational number out? Well, from the previous page, we learned that root 3 times root 3 is, of course, just 3. But I can't change the denominator of a fraction without changing the numerator in the same way. So I have to multiply the numerator by square root of 3 as well. Notice what we just multiplied by. root 3 over root 3 is 1, right? We're allowed to multiply by 1. That's not changing the value of the expression. In the numerator, we get 6 times root 3. In the denominator, we get root 3 times root 3 is just 3. Of course, I can simplify 6 divided by 3. That gives us 2. 2 root 3. And I don't know about you, but I'd argue that 2 root 3 looks simpler than 6 divided by root 3. They have the same value. If you want, you can check it on a calculator. They're the same number. It's just that this one is simpler because we've rationalized. Let's try it again with this example. We want to rationalize. We want to get that radical out of the denominator. Let's multiply the denominator by root 7. Well, that means we have to multiply the numerator by root 7 as well. In the numerator, we get 4 times root 5 times root 7. That's 4 times the square root of 35. We can actually use our multiplication property here since we are dealing with real numbers. Root 7 times root 7 is 7. In this example, we couldn't simplify any further, so we're done. 4 root 35 over 7. You may or may not argue that that's simpler than the original, but it is considered a simplified version because we don't have a radical in the denominator. We have a rational number in the denominator. So there are some basics with multiplying and dividing radicals. In terms of simplifying, it's usually easier to do your multiplication or division beforehand, but you have to be careful to be sure that you're dealing with real numbers. Also, rationalizing the denominator might be a brand new skill for you, something to get used to, but we do want to make sure that we know how to get a rational number in the denominator, what form of 1 to multiply. Good luck!